Okay, it's time to begin. Thank you for all participants who are here now, and I'm from behalf of the organizing committee tell you hello, and now we begin our session, and we have today only one lecture. It is Dr. Dmitry Legatiuk, and he is from Weimar, Germany, Bauhaus-Universität, and his talk entitled as Discrete Hardy Spaces for Bounded Domains in Rn. This talk is plenary talk and will be translated tomorrow in the Yakut when in Europe it will be deep night. And okay, thank you.
Okay, thank you very much, Yuri, for possibility to talk and for a nice introduction. Unfortunately, I'm not in Yakutsk now. No chance to eat straganina, but I hope next time we can do it again. Yeah, I will speak today about discrete Hardy spaces for bounded domains. That's recent work in cooperation with Bauhaus-Universität, Uwe Keller, Anastasia Legatiuk, and based on our recent papers, I will explain a bit more. But let's start with a general introduction and what it's all about. Okay, yes, I can click. Okay, if we look more generally for boundary value problems in mathematical physics, then of course in very general form we can then describe simply by saying, okay, we have a simply connected domain, simply connected at the moment just for simplicity, and we have a sufficiently smooth boundary. Well, and in general we have then system of differential equation plus boundary conditions which are stated on the boundary, and L is a differential operator or system of operators if we have, let's say, coupled problem, and R is a boundary operator, or again, several boundary operators if we have a mixed boundary value problem. And if we look on solution side, how to deal with boundary value problems, then of course, very generally we can subdivide methods in analytical methods, series expansion, methods of potential theory, function theoretic methods, etc. And numerical methods, finite element, boundary element, finite difference method, and any other fancy FEMs. And what's important to remember from numerical methods that we have a discretization step, which is absolutely necessary. Analytical methods, of course, provide us exact solution, explicit formula, and allow to deal with singular problems. But of course, it's well known that we are restricted rather to simplified geometries or idealized, better to say, geometries. But practical applications require more general shapes. So, but numerical methods, on the other hand, of course, provide flexibility so that you can address arbitrary geometries, but they, of course, provide only approximate solutions. And if we go back to discretization, then of course we need to keep in mind that we have in fact two levels of discretization. We have discretization of geometry at first, then we need to discretize the continuous differential operator, and of course then we have to study what's going on the discrete level. We need to study approximation error, how good our basis functions approximate the differential operator in a certain function space. We need to study consistency error, how if the discrete problem represents continuous one in limit, and of course we need to study numerical stability. And another challenging aspect is of course to deal with singular problems by numerical methods. They generally require a lot of adaptations, or as well that if we are interested that certain physical quantities need to be preserved exactly then this can be quite challenging by using classical numerical methods. Therefore, in recent years, the alternative approach became very popular to formulate problem directly on the discrete level. Instead of approximating continuous problem, we shift everything to a discrete level. And in that case, all necessary properties of PDEs are preserved exactly on the discrete level, of course, in a discrete sense, exactly. From known approaches, very old, classical, I would say, conservative difference scheme introduced by Samarsky in one of his books, where he also aimed at finite difference method, which preserves certain properties of continuous problem. Then, of course, discrete potential theory, Rabin-K, who has introduced it. Then, of course, Klaus Gülebeck worked on it, Angela Hommel, nowadays Anastasia also deals with it. And it's in COF, for example, it's where we shift classical potential theory to the lattice. And then discrete function theory, that's, of course, classical complex analysis of function theory, moved to a discrete setting again, works of Gülebeck, Sprosek, go in that direction, and discrete Clifford analysis as a higher dimensional extension of the classical complex analysis, and now also in discrete setting. And that's what I will talk today about, mostly with discrete Clifford analysis. As a parallel branch, one should not forget, of course, the general theory of discrete analytic functions, but that's goes back to the 50s already, and general study of difference operators. But nowadays, it's used more for, let's say, applications in probability, also related to graph structures, and not looking really on the function theoretic aspects of it. And from 2006, introduced by Douglas Arnold, exterior calculus approaches, particularly exterior calculus, finite element method, exterior calculus became very popular, where you move classical FEM to the lattice, and you use tools of algebraic topology to deal with the problems. Okay, today I will speak about discrete function theory and discrete Clifford analysis, but of course I will do it in a higher dimensional setting, and to glimpse general idea at first, that we have a functions defined on the lattice. We use finite difference as a basic tool, and we need discrete fundamental solutions of discrete Cauchy-Riemann operator if we speak about discrete function theory, or discrete dirac operator if we speak about discrete Clifford analysis. And then idea or aim is that construct discrete analog of the complex function theory and its spatial extension in case of discrete Clifford analysis. That we have tools of function theory such as Borel-Pompidou formula, for example, Cauchy transform, Cauchy formula on the lattice, and that will be the main topic today. And of course, advantages, as I said, tools of function theory on a discrete level, and important properties of differential equations or some solution properties are satisfied exactly on a discrete level. And of course, since we are working on lattices, everything, the geometrical restrictions are very weak. So, okay, to say about works in discrete function theory and discrete Clifford analysis, if you look at most of them, then one can say generally that discrete function theory provides, constructed by Gülebeck and Hommel, provided a lot of explicit expressions and explicit formula how to calculate discrete operators, but that mostly in 2 dimensions. And they have addressed, of course, boundary value problems in 2 dimensions. It's a laboratory tool, but in higher dimensions, it's still a lot of things to deal with. And if you look on the works in discrete Clifford analysis, then basically problems in the half space are addressed. But of course, practical applications require tools to address spatial problems also in bounded domains. And our aim was to extend or to develop, better to say, basis to solve spatial boundary value problems in bounded domains by tools of discrete Clifford analysis. And I will show you today recent work, as I said, in that direction, how to construct discrete Clifford analysis for bounded domains in Rn. So, okay, we start With a lattice, we have n-dimensional Euclidean space with basis unit vectors as classic. Points are all defined, and we introduce for positive h a so-called uniform lattice, and h is the lattice constant or step size, h to 10. And basically to say that we have all points are now discrete in our space. Next, since we want to address bounded domains, we consider first the continuous bounded domain omega, bounded simply connected domain with piecewise smooth boundary, partial omega. And then we introduce the discrete domain omega h, a simple intersection of continuous domain with our lattice. In our way to say that points belong to omega h only if we belong to the intersection. So next, of course, you need to classify. If you have a lattice, you have bounded domains, and you need to classify what kind of points you have, especially if you want to address also boundary value problems in interior and exterior, you have to classify. That's why next step is to distinguish between interior and exterior discrete domains. For given this domain omega h, the following objects are introduced. We have a discrete complementary domain defined in classical way. We have interior, denoted by int omega h, is a set of all points such that at least one of its immediate neighbor point also belongs to omega h. And the exterior of omega h, denoted by omega h x, is defined symmetrically as the interior of a complementary domain. So, in the first work in the discrete domains, for discrete domains in discrete Clifford analysis, we have addressed domains, basically three-dimensional cubes. And then we were working with explicit constructions of how different parts of the boundary look. But of course, if you address general domains, for each given domain, it is still possible, but for arbitrary, it comes with very bulky calculations. That's why we decided recently to switch to more natural, whatever it means, and topological definitions of points, exactly like here. In the end, I will show you some references where for two-dimensional cases, for example, all geometrical discussions are done more explicitly and elaborately, where you can, if you want to program it, you can take it and just use it directly on the computer. So next step is to classify boundary points, because now, since we're in discrete setting, you have a curved boundary, for example, you have a lattice, square lattice, but of course, not all points hit exactly the curved boundary, and then of course you have to distinguish what kind of boundary you have. And in discrete case, we introduced then three-layer boundary structure. You have inner boundary layer, middle boundary layer, that's basically corresponds to the true boundary of a continuous problem, or somehow approximates the true boundary, and exterior, that's necessary for formulating problems in exterior domain. So again, we use idea of topological definitions. Okay, we have a point mh is a point of the inner boundary layer gamma h plus, if at least one its neighbor point does not belong to omega h. The point mh is point of the middle boundary layer gamma h star if its neighborhood contains points belonging to omega h as well as to its exterior. And points for exterior boundary layer are defined basically symmetrically to the inner boundary layer. For example, we have a half space, classical case in discrete Clifford analysis. Then we have omega exterior is of course lower half space, and we have omega h plus, the interior boundary layer, that's a layer corresponding to the 1 mn index equal to 1, that's also called one layer. Gamma h star, that corresponds to the index mn equals to 0, also 0 layer, and gamma h minus, that corresponds to mn equals to -1, -1 layer. Okay, next step, we need to define finite differences. We use a classical definition, so forward and backward differences. And for simplicity or generality of constructions, we also need characteristic functions of our domains. So defined classically for interior and exterior. Next, later on, when we discuss also discrete Riemann problems, we need to define before that boundary generators and trace operators. And for that, we also need to address the question, how do we approach the boundary, in which direction? And to do so, we use the characteristic function and application of finite difference operators to the characteristic function. And we say that MH is relevant in the J direction whenever this application of finite difference to characteristic function in that direction is not vanish, doesn't vanish. And then that suggests a splitting into two parts, 0 and 1. That's basic idea presented in this picture. So you have a domain here with omega h, and now we need to say what is actually h plus, what is gamma plus, gamma minus, and so. And if we go along this direction, we cross this boundary here, then we say, okay, we have here 0, and here is a component 1. That's how the splitting works. After that, we can characterize boundary points differently. We have a following lemma that simply, based on the idea of application either forward or backward difference operator on characteristic function in a certain direction. And that gives us another characterization of boundary points. Okay, next idea is of discrete Clifford analysis is, of course, to introduce discretization of a dirac operator, better to say, to introduce discrete dirac operator, which factorizes the star Laplacian delta H. And to do so, Zoman and his co-workers introduced the idea that we split each basis element into two elements, ek plus and ek minus. That's corresponding basically to forward and backward directions. And in order to construct a calculus from that, we need to enforce the following relations given here. And then in the end, if we allow complex coefficients, then we have a complexified Clifford algebra Cn shown here. Finally, of course, now we can introduce the discrete Dirac operator and its adjoint operator dh plus minus by help of splitting of basis vector and finite difference operators as shown here. And the idea is, as I said, is to factorize a star Laplacian, and it's easily to verify that such a factorization holds, where delta H is a classical star Laplacian. So, and in the end, of course, we will also work with discrete monogenic functions, which are nothing more than functions which are in the kernel of a discrete Dirac operator. Okay, we are ready now to move on. And as a first step in our construction, we need to work with discrete fundamental solutions because, as I said in the beginning, if we speak about discrete function theory, then we need discrete fundamental solution of the Cauchy-Riemann operator. And if we speak about discrete Clifford analysis, then we work with discrete fundamental solution of a discrete Dirac operator. We have a classical definition that the function EH minus plus is called the discrete fundamental solution of discrete Dirac operator if it satisfies the classical definition where delta H is nothing more than a discrete delta function. Then, of course, for H going to 0, that's approximately the continuous delta function. Okay. There are many ways how to construct the discrete fundamental solution. The classical is, and which we will follow, is we use the discrete Fourier transform. So we have a discrete Fourier transform defined in a canonical way over hypercube minus pi over h till pi h. So, and the inverse transform is given by restriction of the standard classical continuous Fourier transform. There, RH is a restriction operator, and F is, as I said, it's a classical continuous Fourier transform in Rn. Okay, now, since we have a definition of discrete Fourier transform, it's easy to calculate the symbol of a star Laplacian by knowing the symbols of the finite difference operator, and we get the classical symbol here, which was studied a long time ago also by Stummel, for example, in his work on general elliptic operators, and by many other people as well. So, thus we have such a relation, and from that we can say how look the symbol of the Dirac operator, of the discrete Dirac operator, and formally we can write now the how looks the discrete fundamental solution of the discrete Dirac operator. It's basically we take the continuous Fourier transform of psi of this guy here divided by the symbol of the Laplacian, and we calculate its restriction to the lattice. It's not a question how to calculate it practically. That's another story. At the moment, we want to have a nice theory and how to bring it on the computer. But as I said, it's another topic of research. It's another line of research. Okay, some known lemmas. The fundamental solution satisfies, first of all, the definition. That means that the EH minus, here should be subindex theorem, EH minus plus is indeed discrete fundamental solution, and that of course belongs also to the P space. And lemma 3 it shows the estimate of how good the discrete fundamental solution approximates the continuous fundamental solution of the continuous Dirac operator. That's known estimate, also was constructed in one of the papers by Bauhaus-Universität, as well as by in setting out discrete clifford analysis by Zoman and Uwe Keller. So, okay, after that, since we know now what's a discrete fundamental solution, we can move on. And move on means we introduce at first the discrete Stokes formula. I will present, for Stokes formula, I will present both for interior domains and the next slide for exterior domains, but later I will restrict only to interior domains, although all results in all papers are also presented for exterior domains. But due to time limitation space, I will only speak about interior results. Okay, so we have a discrete Stokes formula. As I said, here you have a term, summation goes over whole space, because we have here our characteristic function, and then of course it's allowed more flexibility. In our first work in that direction, as I said, we were addressing hypercubes or three-dimensional, since we were speaking about R3 with just normal cubes. And then where we have constructed everything explicitly over all boundary edges, but of course for arbitrary domain is if you have a given domain, that's always possible. Of course, it's very long calculations, but it's possible. But for general theory, it's much more flexible and much more easier to work with characteristic functions like here. So, and then we have this guy that's a summation over different boundary parts where we have to distinguish between relevant directions again. And then the only condition we have that for all discrete functions f and g that the series converge. Since we're in discrete setting, that means nothing more that function should be in a P space. That's the advantage of a discrete setting. So analogously, we get the discrete Stokes formula for exterior domains. Same principle, same idea, only some slight modifications because different directions now became relevant. And of course, you need not forget to have a characteristic function for exterior domain. Okay, after having discrete Stokes formula and using, instead of function g here, the discrete fundamental solution, we obtain immediately the discrete Borel-Compu formula. That's arguably the core of the function theory in general. So you have, that's, as I said, that's for interior. In a paper, you can also find the same formula for exterior. So what's going on here? This is summation over domain, because you have here the characteristic function, and that corresponds to the boundary part. If you, as you know from a complex analysis, this can be formally be associated with the T operator or Teodorescu transform, and that's nothing more than Cauchy type, Cauchy integral. So Yes, that already brings us to the next. After having discrete Fourier compu formula, we can immediately present the discrete Cauchy formula shown here. And after summarizing all parts together, we can present the discrete inner and outer Cauchy transform. So then for LP functions defined on boundary layers.
5 minutes.
Yeah, I know, I have a timer here, thank you. I will speed up, yes. So, okay, so we have a discrete Cauchy transform, and important is, next step is to study properties of discrete Cauchy transform. So, for that, we have a following theorem proved in the paper. So the interior and exterior Cauchy transform have the following mapping properties, that we map LP space from a boundary, two-layer boundary always, either middle layer plus interior or middle layer plus exterior to the interior, LQ in interior, or to LQ in exterior. And of course, properties 2 and 3 show nothing more that we get by applying interior or exterior Cauchy transform discrete monogenic function, either in interior or exterior as expected. Okay, next, we need to introduce some further notations to shorten calculations and shorten formula. Sometimes we will use explicit notation with underline, means nothing more that underline xi, all components of xi till nth, because sometimes we need explicitly the nth component. So, and to introduce discrete Hardy spaces, we need the Planetary formula, and for that we also need RISC kernels to be introduced. A typical approach to work with to introduce RISC kernels is to work with the corresponding Fourier symbols on boundary layers. In the last paper, we showed calculations for that, and that's of course also people who know pseudo-differential operators goes along the line how it works, where it can be done, but it's very technical. And for arbitrary geometry, it's complicated. Instead, we use a classical trick from a continuous case where we say, okay, there exists a mapping from a real line to any part of the boundary, and then we use this trick. But we calculate Fourier symbols over real line, and then we map them to, of course, we don't know exactly the mapping, but that's just a formal approach. So, and then we have RISC kernels defined here. That's n-1 f. It's n-1 dimensional Fourier transform, and phi, it's the inverse mapping of individual boundary parts to the real line. Since we're in a discrete setting, that means nothing more than rotation and translation of our domain. Okay, after that, we need to introduce the pair of discrete operators, shown here, that way fulfills the projection properties. And then we are ready to define the discrete Hardy spaces. The space of discrete function f, both discrete n-1 dimensional Fourier transform, fulfills such a relation on gamma h plus is called the inner discrete Hardy space, denoted by hp plus, and analogously we get the exterior Hardy space. So now we have a Planetary projection or Hardy projection, p plus, p minus. And now, for Riemann-Hilbert problems, we need to introduce some machinery by introducing extension operators. So, which extends a function from the interior layer to the middle layer, and we have same extension operators for exterior case. So, it's given here. After that, we can define the trace operator, which is nothing more than maps a function from a domain to the two boundary layers, interior and middle layer, or exterior, the opposite one. And the complete trace operator is summation over all parts of the boundary. So projection properties are studied and they are as expected. And finally, we are ready to define boundary generation, which are a speciality of the discrete setting that act on the functions either on gamma h plus or gamma h minus. So we basically generate function on two boundary layers from one. That's the idea. Again, then we can characterize Hardy projections by introduced notations. And finally, we are ready to discuss the discrete Hilbert problem. I will show you 3 of them. Just we have a first problem. We have a discrete monogenic function in omega h. We have a boundary condition, and solution of this problem is given explicitly by the following theorem, again by using Cauchy transform and boundary and the boundary generator G plus. So discrete Hilbert problem 2. Again, we have a discrete monogenic function, and everywhere except the one middle boundary layer, and we have such a jump relation on the middle boundary layer. This theorem for 9 gives the solution of this problem. And similar, finally, we have a discrete Hilbert problem 3, which is basically unique for the discrete setting, since we can formulate now boundary conditions on 2 layers if necessary, relating boundary conditions on 2 layers, which is only possible in a discrete setting. Yes, so that's a solution. Again, in terms of our extension operators and all machinery I have introduced today. So, okay, as a short summary, so discrete function theory and discrete Clifford analysis aims to develop function theoretic methods on the discrete level. So the new results in discrete Clifford analysis for bounded domains in Rn have been presented, and the theory can be used to solve discrete Hilbert problems. So from my literature, just to mention a few papers, of course, discrete Clifford analysis by Prax, the Shepard-Zone, Van der Voorde, discrete Hardy spaces. This is our 2 papers on which this presentation is based on. Then Gürlebeck-Hommel, of course, several papers of them, and several papers of Anastasia. That's particularly where if you want to see how to discretize geometry constructively, that's I would recommend to read that one. And here, for example, how to do discrete function theory on the rectangular lattice, which is much more interesting than square lattice, but of course also much more complicated. Okay, thank you very much for your attention. And in Yakutian, I guess, Mahtal.
Thank you, Dmitry. Nice presentation. Any questions and comments? Dmitry, I have one question.
Yes.
Let us imagine one situation. One can to solve some boundary value problem by 2 methods. One of the simple usual finite difference method, and the second is presented method. But in the last step, when you must to do numerical implementation, you must to solve some system of linear algebraic equations.
Yes.
And what have to say about this system in usual finite difference method and in the geometry? Have you missed some benefits for numerical solving of this linear system algebraic equation, or?
I can tell you the following. Discrete Clifford analysis, unfortunately, numerically has not been studied so well. But I can refer to works in discrete potential theory and discrete function theory in 2D, where it has been observed that it converges faster. You don't need so many points, and stability is better by the method in comparison to finite differences. But for discrete Clifford analysis, that of course has to be still studied. But the hope is similar, that of course you get full system of that's not really sparse, but stability is still better. That's the hope.
Okay, thank you. I see. Okay. More questions, comments? Ilya Ivanovich?
May I ask 2 questions in Russian?
Yeah.
It's simple questions, so from answer it will be clear what I've asked. Вот такой вопрос. Неужели омега, вот эти области, да, они могут отличаться от параллелепипедов? То есть таких
No, of course. I mean, that's a good point, because when you are in discrete setting, in fact, you can always argue that any discrete geometry, it's always composition of parallelepipeds or cubes. That's true. But of course, since you have a curved, let's say, surface in 3D, then of course you need to and you have a square lattice. Then you will have a composition, of course, of a lot of the small cubes, and you still need to classify what kind of point it is. But that's the main challenge. That's the main challenge.
See. So it's approximation series. It's unproven yet. It will be proved. I think when
no, we have convergence theorems. We also have that's proved. But I mean, for classification of geometry points, you still need to make clear what if it's boundary points, if it's exterior, if it's interior layer, exterior layer. That's why it's some specialities for discrete case.
I mean, if we have complicated domains, so these solutions of these systems will be much more different from real solutions, isn't it?
I mean, we have a convergence for if step size goes to 0, you get a convergence to continuous solution. That's why that's like in any numerical method. In that regard, it's a consistent scheme.
Okay.
И вот второй вопрос. В какие годы примерно были разработаны вот основы этой теории? Там 70-е, 80-е, 90-е?
Я начало вопроса не услышал, извините.
А в какие годы были
what time? Okay. Let me just go to the slide. Here, for example, I mean, if we speak about conservative difference scheme, that Samarsky did it in 60s, 70s. That was a discrete potential theory, Rabinky in 80s. And function theory also in 80s started. I mean, it depends what do you really, how do you really classify? But if we speak about discrete function theory, my understanding, then it's also 80s by Güleberg. His co-authors, people in Ghent in some parts. And discrete Clifford analysis, that's basically 2005, around that time began the idea. And discrete analytic functions, it also goes back to 50s or even because discrete analytic functions were also studied by Ferrand, and that's, if I'm not mistaken, that's 36 or the beginning of 40s already. But that's another thing. In Moscow, some people also working on it, for example, Dimnikov, but we are looking at the task from point of view of algebraic topology. That's not what we are aiming here. And if you look what I call here exterior calculus, that's finite element exterior calculus or differential forms, then that's also 2006, 2007, where it became the hot topic for numerical people.
Okay, thank you.
Thank you very much.
And comment? No question, no comment. Okay, let's thanks our speaker. Turn out your. Спасибо. Okay. Wow. Hello. Where is Klaus?
He has no camera. I'm not sure if he has a microphone even. Because he's in office.
Микрофон не включает, что ли?
No, he doesn't have a microphone.
Sebastian, okay. Where is Klaus?
I don't know. I'm in my office and he's not here. So, as Dimitri said, I think he has no camera and no microphone in his office.
He is spiritually with us.
Exactly.
Okay.
Close to us, but not visible.
Thank you for all for the participants in our small sessions. And this lecture tomorrow will be translated in the many participants in the plenary sections. Thank you, Dima.
Okay, thank you very much.
Yeah, we are finished. Goodbye.
Take care. All the best. Ciao, ciao.
See you in the future.
Yes.